We will discuss about yesterday's topic, which we missed due to some technical issues. So today I will give you a brief overview about the software, this module band, and we will continue with the current topic which we discussed today. So CDCDFT, the response properties for band for crystals with the band module. So let me introduce myself. I'm Srijit here from Nyro Research, currently working as an application scientist covering computational chemistry and physics topics. So So what we can expect from SCM softwares? We need to understand what's the purpose and need for modeling, why the calculations and simulations are important, some theoretical foundation. It's a quick overview about the history and a brief explanation about Amsterdam modeling suite plus the licensing. I think we have covered all the things in the previous sessions. So the first thing, why we should bother about calculations and simulations? Obviously, we need to accelerate our research, reduce cost, time, we need some experimental setups to assist these methodologies. Then we have to focus on the models. What's the accuracy? We need to compare the theoretical results with the experimental results. Then only we may able to fix the accuracy and all, followed by synergy experimental calculations. So this package can be useful to find out the best catalyst, best battery, and even best oil LED methodologies. So this is about the theoretical foundations. I think that there is no explanation required. We are all aware about the things from classical mechanics to quantum mechanics. We all know that from Isaac Newton to Erwin Schrödinger. So I'm just skipping up this slide. So this computational atomistic simulations, we all aware about this Erwin Schrödinger equation. So, sorry. So this is about the electronic structure methods from ab initio to density functional theory through DFT based tight binding, then semi-empirical methodologies like MOPAC, which is known as molecular orbital package, then this Hartree-Fock methodologies, which we discussed. So this is about the representation about how fast the methodologies are. And this graph or this table will brief you how and which methodology can be easily understood by covering the timing and all. So you can see that using classical force fields, we can screen maximum 10 lakhs atoms. Reactive force fields or ReactSFF can screen more than 5 lakh atoms. Semi-empirical methodologies have a limit of 5,000, followed by DFTB. DFT usually screen up to 500 atoms. So these are some of the computational methods and level of theory. So material simulation methods, we need to solve the Schrodinger equations. We can use.
ये जैसे है एग्जैक्टली वही घर में होगा हर बॉक्स सेम तरीके होगा यहाँ से बॉक्स लेना और एक मास्क करना
Excuse me, any questions? Hello. Shall I continue? Hello.
Yes, sir.
Okay, thank you. So in this slide, I will show you that what are the, modules which we discuss in SCM or AMS, Amsterdam Modeling Suite, how to solve the Schrodinger equation, how we can compute electronic interactions in a system from ab initio. So for quantum mechanics, we have ADF, MOPAC, and ADF plus QE, quantum espresso, which covers molecular orbital theory, semi-empirical QM methodologies, and density function theory in QM. And then we have classical force field methods, which we use ReactSFF module for molecular dynamics and Monte Carlo simulations. So this is about the atomistic modeling, which covers the timing as well as the different modules. What are the different purposes? For example, today we are discussing about QMMM as well as the band properties, which covers the periodic DFT calculations. Obviously, for molecular DFT, we use ADF module. For molecular dynamics, we have ReactSFF. So these are some of the representations of how much time it will consume within the fraction of the time. So we have this is a representation or the pictorial representation of our modules and the software requirements. Before I proceed to that, I have to say what are the areas which are applicable for these methodologies. From inorganic chemistry, we can use various different methodologies. It can be applicable for material research, polymer research, modeling, and also in pharma for nanoscience, catalysis. All these options can be useful. So this is the overview about our Amsterdam modeling suite with the various modules from ADF, BAND, DFTB to PLAMS, which we use for Python scripting workflows. So the ReactFF module is used for dynamics of large complicated systems, DFTB for fast electronic structure, and ADF for spectroscopy, advanced solvation, and bonding analysis. When we have for fluid thermodynamics, we have this Cosmo RS module. So today, first we will discuss about the periodic DFT methodology, which is known as band. So this is the representation of our band uh, module. So we can see the main panel followed by the properties window. And in properties, we can see what are the different calculations we can do, plus with the details level of calculations. So before I proceed, do you is the program running successfully in your machines? Did you install successfully? Hello, answer from your end. Is the program running successfully in your machine? Okay. So these are some of the publications which we have published with these methodologies. And this is about the AMS environment where we can do material modeling, the different theory levels like DFT, DFTB, the different properties of the molecules which we can focus on from structure to energy, electronic optical properties, mechanical and thermodynamic properties, the methods from energy minimization to transition state search, reactive dynamics, the different tools which can be useful for building crystals, surfaces, molecules, interfaces, and also polymers. The visualization panel for visualizing the structure, band structure, the dispersion correction, and the density of states, and also some force field generators. So this is about the overview of our AMS environment. And this is the properties, material properties, which we can focus on with the help of this interface or this software. So it covers structural properties, some thermomechanical properties, thermodynamic properties, which can be calculated using Cosmo RS, then the chemical properties, transport properties, and electronic, optical, and magnetic properties. So today we will discuss about the optical properties with the help of time-dependent current DFT methodology. So I will just go to the software. So this is about the hardware requirement. I think in the first session, the SCM team has given a briefing. So I will just repeat. Minimum we require a RAM of 2 GB, recommended 4 GB, and we require minimum physical cores 2 core. And with the 64 GB RAM, we prefer minimum i7 or i9 for the better calculations. And the following is a benchmark representation of our HPC calculations, which is available in our website. So you can check it or we can share the details to you. So so I will just go to that demo. So is my screen visible? The AMS window?
Yes, sir.
Okay, thank you. So before I proceed, are you facing any issues during installation of our software in your machine? This is the third time I'm asking the question. No response from your end? Sorry, I didn't hear anything. Okay, we will assist you if you face any issues. Okay, let me show you this. Okay. First, we need to create a directory to. Hmm, okay, I have given a name. Oh, it's already existed. Okay. Okay. So we will create Demo 2023 and we need to create the new input here. Okay. So as I told earlier that today we are focusing on the optical property. So this time dependent current density functional theory or TD-CDFT, it's a theoretical framework for inputting the optical uh, response properties such as frequency dependent dielectric functions. So in this section, we will cover the implementation for extended systems like one dimension, two dimension, or three dimension in band described. So the input keys can be described in new response or in old response, but here we are focusing on new response methodology. So if you are interested, you can try along with me also. So first, this is the input interface which we are going to create our molecular structure. First, we need to change the interface to band, I mean the engine to band. And then we need to select the molecule from, okay, uh, first we will go with the silicon. silicon. So silicons, okay. So in a single click, you get the silicon atom, and then we need to build the crystal. So click the view to the periodic. So periodic view type. So repeat unit sets. So we will get a molecular system. And the second step is run a single point calculation. So we need to set the basis function to set to be set B, and then we need to create this two things, and then we have to go to details where we have to set the k-space integration. So the accuracy should be 3, and then we need to save this file. So I'm just giving a name like LDA underscore. So I'm just saving it. So now the input file has got a name, and now I'm just clicking it to run. So you can see that the program is running, and it will take some minimum time. So you can see in the meantime we can check the log file. So in the log file itself, we can see that the CPU timing and all, how much CPU time is it taking, initial density. So within few seconds, that job will be finished. So in the meantime, is anybody doing the same steps with me? So once it is finished, it will automatically, yeah, now it is finished. So once the job is finished, there will be a red color, and we will go to first the SCM icon. We can see the log file. So you can see the normal termination. There is no errors. So energy of formation, the charges, Fermi energy, band gap, and also in SCM we can check the band structure in a single click. So this is the official outcome of the band structure. You can save the band image, density of state image. So the lattice vector, and also the step is not finished here. We need to continue the next method step to run an old response calculation. So I'm just skipping this thing. So first, again, we need to go to the band panel. So we need to untick this band structure and density of states. And then we need to go to the properties. So here we have to check the dielectric function, TD-CDFT. I told in the beginning that we are going to calculate that property. And then we have to change the method. So here the method from none to old response. And we have to set the frequencies. So the frequencies, number of frequencies should be, so default 3131. Starting frequency. Sorry. It's a mistake. And here we will do 231. And then the rest is the same. We will save it again, but this time we will select as save as. And then we will run the. Oh, so it will take another few minutes, and in the meantime, we can check the log file. See, the main methodology is that the main point is that whatever be the inputs we are giving to this interface, that should be clear. If there any issue happens with the inputs, definitely the system will define the error. So you can see in my interface that some errors, these are the errors generated when the setup went wrong. So now you can see that how the calculations are going now. Maximize the screen. So, and once the program has completed, you can see. So you can see that how much processors it is taking. So we can. So in this sequential view, you can set the number of processors also, or the number of cores you can use, because my machine is an 8-core machine. So I can set the number of physical cores here for the calculations. Right now, I didn't set any calculations, I mean, any cores. So once it is finished, we can go to check the spectra. Are you able to see my screen?
Yes, sir.
Is anybody doing this process along with me? The next thing is QMMM studies. Nobody is answering. So once this is done, okay, let the process continue. We will check with. Anyway, we will share the results and all the files to you for your uh, exercise and all. Bring things. So in the meantime, I will show you how to create the inputs for our QMM calculations. So let them go like this. We'll create a new directory and we will give a name as demo. And then, so here, so inside the directory, you can create a new input. Okay. So here we are going to discuss about how we can do QMM using covalent organic frameworks for COFs. So COFs are built of small organic units. There there are infinite ways to assemble small units, but this is basically organic systems are reasonably well described by fast DFTB method. So how we can create a methodology? That's the thing. So first, I have already downloaded a COF file. So I am just importing the coordinates from the downloaded files. So this is the COF which I have downloaded here. So can you see this organic framework? So first we need to define the QM region. For that we need to, one second, we need to select the hybrid engine. Okay. So the things, the calculations we are doing in hybrid mode. So first we need to select the atoms. So we want our line linker in QM region. So you can see two organic aromatic rings followed by this linker. So we are going to select these atoms. So just plus shift. So can you see how many atoms are selected in the interface itself? So total 21 atoms are selected. And now we need to define the QM region and MM region. For that, we must go to models region here. When I added that button, it's already the region is selected. I'm just renaming it as QM. So now I must go to the main band and then I'm just clicking this QM. So this embedding from electrostatic to mechanical, physics and mechanical. So now set the region. We need to set, we already selected the QM region and then we need to set the engine. And then we need to go with the TFTB. See. And next thing is that we need to enable the click on this band region and then We need to go to the unrestricted. Just click here, and then we need to set the basis set. Set P. So DFTB will be the same. So are you able to follow this QMMM settings?
Yes, sir.
Okay. See, I'm asking the same question. Are you doing this methodologies along with me, or just viewing only how the steps are going on?
Yes, sir.
Okay, thank you. Okay, so this is about the inputs which we have generated for this QMMM calculations. So you can see, I will repeat one more time. First, we need to select the, I mean, import the coordinate file, and then we need to select the region which we have to go for the QM studies, followed by, I showed you the region, and I selected the region and renamed as QM, and then I go back to the main panel, and then I have created band engine. So in band, we need to create this basis set and all, and then the DFTB to make these calculations a little bit faster. So in the meantime, before we proceed, let's check what's the story going on in our previous case. Okay. Created so in demo, I think the process is running only. Once it is finished, I will show you. Okay. Uh, yes, sir. We will show the band tutorial as per the time permits. I got a question for yesterday's tutorial. So today, once this thing is finished, we will definitely show the tutorial. So this is the log file for that. It's all running. Okay. So let me save this file for our process. So name. So after saving it, you just click the run. Definitely, it will automatically run the program. So we can see so how many processes are the machine is taking to run this specific hybrid calculation. See, so this is the methodology which is working here. In the meantime, we will check what's the output of our system. Can you show how to define the number of cores for a job? Yes, of course. Sir, I told you once we um, see once you set up your inputs, either you can set the physical cores here. If it is an 8-core machine, you can set the physical cores 4 into 2 or 2 times 4. That's the way you can set the physical cores in this GUI. So this process was finished. See, so we will go to this first process. I think that without any errors, they have completed this uh, program. And I will. So first we need to check the spectra. Okay. So once the calculation is finished, 1 second. Okay. Are you able to see the spectra?
Yes, sir.
Okay.
Yes, sir.
Thank you. Okay. So it's a result of this TD-CDFT from band. One is real and another is imaginary. So we can see the dielectric function. So we can check the spectra one more time. Spectra. See, in TDC, DFT, we can check the susceptibility, polarizability, dielectric functions, and refractive index. So in this case, we have discussed about the dielectric function. So we will go with the XX. One second. See. So this is the official output of that TD-CDFT calculations for the dielectric function. So any questions regarding this calculation? I have given you how to because the inputs which we generate in this interface is the most important thing. What will be the inputs? Uh, so thank you. How to interpret the results and yeah, that's what I'm breaking, sir. So what will be the inputs which we give? I think you understood what the inputs which I have given as per the tutorial which we discussed. So so this is an old response methodology. So in here we have to focus on the frequency calculations. I mean what the correct frequency we have to give and also the dielectric function. What's the property which we discussed? So obviously I told you from the spectra itself, PDCDFT, this much properties we can interpret. So here I focus mainly on the dielectric function. So similarly, we have the new response methodology for similar calculations. So the band gap. So in this method, we just calculate the band gap for the chosen theoretical level. So there should be an experimental. We have to compare it with the experimental bandpath. Then only we may able to fix the accuracy that how much this results are accurate. So hence we will shift the virtual crystal orbitals. So by the value of then this energy space. For that only we fix the frequency range from 2.0 electron volt to 5.0 electron volt. I think you saw it when I have set the inputs. So this is the output. So this gives you how much the machine is faster to give the results in reliable way. Any other questions? So in the meantime, we will share you the PDF of this tutorial as well as the session. I will show you what's the story happening in the other end of our see. We can directly go to the output file. So this is the output file generated by AMS. You can see the version because I'm using the 2022.103. I think this you got the 2023 version. And the single point calculations in iterations. Here the properties, you can see the geometry and also the Mulliken charge analysis, where you can see the basis function charge on axis. One more question, how to build graphene electron in band GUI files? Yeah, I will tell you, I will tell you. I actually got the this query in my mail. I will show you. Yeah, definitely, definitely. Because I need to brief two important properties today. Anyway, I will try my level best to clear that question. Soumi, I think you have mailed yesterday, isn't it? 88 months. Can you specify that question? How can we make customized organometallic bonds, ETA bonds? Yeah, I will tell you. I will tell you. Once this thing is finished, I will definitely answer the queries. Okay. So this is a way that we can figure the outputs, and then we can go to the response properties. It's inactive. Timing, CPU timings, we can see how we can calculate the results. So how much time it has taken, the CPU time, the system time. So this is the way we can screen the output figures of this uh, specific methodology. You can extract this as a CSV file here. You can build a spreadsheet. So this is one method. So one more story is the, so this is our QMM calculation going on for that organic that's here. So here we will check the log file. So it is also running smoothly without any errors. So the main point is that whatever be the inputs you give. This another question. Yes, we can analyze metal organic frameworks. We have the tutorials. We will share you. So it will take some time. So this is the log file which we have. So you can see that the results which are generating in this QMM calculations, the process is on halfway. So if you go with the, sorry, I'm just closing this. Okay. I will show you a symbol how much the results are published here. To go to AMS movie, if we click this AMS movie, we will be able to see how much, see how the process is progressing. It's progressing in 2 frames only. So any questions? Are you able to follow the steps?
Hi, Srijit. There is no audio actually from your end.
Huh?
I was unable to hear for a few seconds.
Right now?
Yeah, we can hear.
Okay. One minute. Okay. Am I audible right now?
Yes,
Okay. Thank you.
is the procedure same if it is for the organic molecule, QMMM analysis?
Organic molecule means this macromolecules.
Ligand is organic, small molecule, and
Okay.
the protein ligand complex.
Will be different, sir.
It's a different one.
Yeah, it will be different.
Okay. So the steps that you have showed now is majorly for inorganic molecules,
Yes, yes, yes. For inorganic.
where the number of atoms are less than 500.
Yes, yes.
Okay.
Any other questions? Is it possible to run a protein ligand QMM in AMS? Yes, sir, we can do.
Is there a session covered in this workshop?
Regarding
Same thing,
protein,
whatever.
protein ligand QMM?
Yes, yes, yes.
No, sir. But we can brief you how it can be useful. So
Okay.
we are using amber force fields for this QMM of protein ligand. Yes, sir, we can arrange a session for that.
Okay. Thank you.
Yes. Any other questions? So what's happening in the interface here? Okay. So when we check the log file, we can see that the program is not fully completed. It will take some more time because it's a bigger system. So we will show you how this output will figure it out for this calculations because we have already run it earlier. So the end product will be once the calculation is finished, it will look like this. And yeah, see, this is the thing which we have done already because it is a time consuming process. For the time being, I'm just showing the results which we have obtained after that complete run. So the inputs which we have given, which we discussed today, the same way, uh, the models, the region, the hybrid engine, the band engine, the same methods. There is nothing different, the same basis set. Because since it's a big network, so it will take some time. So I'm just showing you how we will get the output and all. Just click the movie. So this is the method. See, it takes almost 600 plus iterations, almost 624. So once you click the run, it will be shown like this. You can see the variation here. So this is the dynamics of that QMM calculation which is running. That's the frameworks. You can see the energy, gradient max and the gradient RMS. So this is the output which we will get after the calculation. And we can see the band structure. One second. This is the output. So it will form a bond with the ring systems. Can you see this? So this is the inorganic linker which links with that organic framework, and then end of the uh, process it will be like this. There will be a bonding between that ring systems and this linker. So this will be the expected output of that specific methodology. So any questions? We will share the PDF as well as the results to you. So this is the calculations are running smoothly. It will take some time to finish. So any questions? Are you able to follow the steps? Is it possible to carry out DFT analysis of polymeric nanoparticles? Yes, of course. Any other questions? We have a, we are about to finish the process and all. So that's why I'm asking me further questions. So we have covered that two tutorials today, band as well as this QMMM calculations with an inorganic framework. So I have discussed about the. Can you please share the details of all modules and aims? Yes, of course, I can share the details. Yeah, I will show you one by one how we can. Yes, 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 I will show you. So modules in the sense means, 1 second. So mine is the 2022 version. So this is the interface which we can do all our works. So this is the ADF engine in AMS, and in ADF in this panel, if you click, you will get all the modules. So these are the modules which are available in my interface. We have ADF, band, DFTB, force fields, then ML potentials, Leonard Jones, MOPAC, molecular orbital package, then reactive force fields, hybrid, conformers, QE and WASP. These are some interfaces indexed in this methodologies, followed by which what are the different tasks we can select. We can give single point energy calculations, molecular dynamics, potential energy surface scan, then the single point energy calculations, transition state search, then the spectral calculations. So in the next sessions, we are going to discuss about the spectral analysis, H1 NMR spectrum with the ADF module, followed by we will go for one polymeric bond boost methodology, a copolymerization step, and we will check the dynamics also using React Surfer. So I think after a couple of days, we have the next session will be on October 2nd. So on that day, we will discuss about the NMR, and on October 3rd, we will discuss about our one boost methodology. So this is about the overview about our software. I will show you a single. So you can see how to. Am I audible?
Yes.
Okay. So you can how you can load a molecule. There is a database itself here. Second. You can search your molecule here, or you can draw your molecule from this. You can select atoms. Either you can. So this is a method how we can draw it from scratch, or you can import your molecule from this database. For example, if you click benzene, so it is available in molecules and also in crystals. We have crystal database here, and also the molecules. So in a single click, you can add the molecule to this interface. So this is a one method how we can use optimize. I will just run a single optimization. So you can select the symmetry, and also you can do pre-optimization. So symmetry is selected T6H, and I'm just running the DSLP. The rest are the is selecting as a default, and then I'm just saving it and giving just sorry. Just think it is not able to save in this. Okay. Sorry, I found them. Okay. So I have saved the file and now it is running. So you can see simple geometry optimization in the ADF. So this is one way of calculation. How we can, the only thing is that you need to select the module, which engine you should go for the calculations. For periodic calculations, you have to select band, and molecular DFT calculations, you can select ADF. Then for this molecular dynamic calculations, we can use React support. So like that, the overview about our software. Any other questions?